Hello, welcome back everyone. In this video, we will be exploring the concept of optimization in a calculus context. So I don't know if you've had a chance to check out my other video on optimization that uses mainly algebra tools. The process is fairly similar, but using calculus actually makes it much easier for us. It makes the work much faster. The tools from calculus prove highly useful in situations like this one. So if you haven't seen the Algebra 1 video, I recommend you go and check it out first so you get a basic idea of what it is. Like I said, it provides a context of Algebra 1 within the concept of optimization. We use tools from Algebra 1 to help us optimize. So let's just do a quick refresher on what it means to optimize something. What does that word mean? Well, it means to change some certain characteristics in the system to get the absolute best outcome possible. And within a math context, it typically means to find a maximum or a minimum. So this will just provide a really brief example on what it means to optimize something and how to find either a maximum or a minimum. So I have a problem that I thought was pretty interesting. They want us to find two positive numbers whose product is 750. So if our numbers are A and B, then A times B must have a value of 750. And for which the sum of one and 10 times the other is a minimum. So they already give us the thing we want to minimize right off the bat. We want to minimize the sum of 1 and 10 times the other. So it doesn't really matter which order we do things in. Let's just say we have 1, which is A, plus 10 times the other, so plus 10B. This is the thing we're trying to minimize. Every optimization problem has a quantity that we're trying to optimize. In this case, it would be A plus 10B. They ask either to maximize something or to minimize something. In this case, it's minimize. So this is the thing we're trying to optimize. And we also have a constraint which appears above. A times B equals 750. This is our constraint because it limits our outcomes we could possibly have. We know, for example, that A being 10, for example, and B being 5 would not work because those two do not multiply to 750. We have to make sure that we abide by all of these specific conditions to get our real answer here. So this being a first semester calculus video, you probably imagine that it's going to involve a derivative to some degree, and you're right. We're going to need to create some kind of a function for the thing we're optimizing, and then use our calculus tools to find the best possible value, find the maximum or the minimum. So we want to minimize this quantity right here. So we want to somehow create a function with this because we can't really take the derivative of something unless it is a function with a definite value. So in order to create a function with this, we have to use our constraint. We have to be a little bit creative in how we do this. We want to take this entire thing and put it in terms of just one variable. We want it to be either only A's or only B's. So I think I want to keep everything in terms of A. So what that means is I want to take our constraint, A times B equals 750, and then I want to solve for B, which yields the following. We get B is 750 divided by A. So now that we have this definition of B, a quick substitution would yield the following. And then I want to create a function because it's kind of hard to understand what's really happening here in a calculus context without having a real function that we are working with. So I think, well, this is a sum. I think I'm just going to call it S of A because A is our variable. In reality, anything would work depending on the variables. Typically, we see f of x, maybe g of x, maybe something like y of theta if there's some trigonometry involved. But those are all just merely formalities. And this one I decided to just stick with S of A. So we want to find the derivative of this. And the reason we want to find the derivative is because remember what derivatives do. Derivatives provide us with the rate of change of a function. So in order to truly find the maximum or the minimum quantity of anything, we want to maybe just explore what it means graphically. So I want to use a graph to explain this real quick. So we can tell that on this interval, I want to maybe just draw a box around this particular interval I have in mind. This interval right here. So if I asked what the maximum would be on this interval, we could pretty easily trace the graph from both sides and determine that it doesn't ever get higher than this point. And the same thing for the minimum. If I asked you to find the minimum of this graph, it's pretty clear that if we were to trace the graph from left to right, and then also trace it from right to left, it's pretty clear that we don't ever dip below this point right here. So this has to be our minimum. This has to be our maximum. So this is just a quick graphical intuition on what it means to find the maximum or minimum of a function. But how the heck do we find these points without a graph? I mean, with a graph, it's pretty easy. We just figure out that this is the highest point and then this one is the lowest. But what if we don't have a graph? What if we just have a function? The way we do that is using a little bit of calculus. We use our tricks from first semester calculus. We take the derivative of this. And if our derivative is 0, meaning that we have a horizontal tangent line, for example, if this function is f of x, this would be f prime of x is 0 at this particular point. Same thing goes for below. The thing that these 2 points have in common, the thing that the max and minimum have in common would be the fact that they both experience a 0 derivative at this value, at these 2 particular values of x. Let's say maybe x1 and x2. So we've just found out that all we really need to do is find the place where the derivative is 0 and it helps us find the maximum and the minimum. So we already have our derivative, or sorry, we actually don't have our derivative yet. We have a function. So what we want to do now is we want to take the derivative and see if we can figure out the locations where that derivative is 0. And again, this picture is completely unrelated to the problem at hand, but I thought a graphical example of what's going on here might be nice to have, might be nice to help us understand the concept a little bit better. So we have S of A. We want to find the derivative, but before we do that, you know, I'm kind of picky about this kind of thing. I might just simplify this, make this 7,500 divided by A. This isn't necessary, or I guess if you have OCD like I do, minor, undiagnosed. I haven't been diagnosed, but I still think I have it, OCD to some degree. Then you may want to do something similar. Not only that, it makes the derivative a little bit easier to find. So the derivative we know is f prime of A. So A is just a single variable. The derivative of a single variable is just going to be 1. And then we have this right here. We have 750 divided by A. We want to find the derivative. So we're going to need to use the quotient rule. And just as a quick refresher, if f of x is u over v, then the quotient rule for derivatives states that the derivative of this rational function would be the derivative of the top times the bottom minus the top times the derivative of the bottom. And then we're going to have that over the bottom squared. So in this case, u would be 7,500, v would be a. So we want to do the derivative of the top, which is 0, makes the whole thing 0, times the bottom minus the top times the derivative of the bottom. The derivative of a is 1, all over the bottom squared. So we can simplify it a bit. We have 1 minus 7,500 over a squared. So this is our derivative. this is one of the first things we cover in the introductory chapter on derivatives if you're taking calculus for the first time. We first learn how to take derivatives, and then we learn how to use them and apply them to solve complex problems in the real world. We have our derivative, and just a reminder, we were interested in the place where the derivative is 0. So we have to set our derivative equal to 0 and then find the value of a that gets us that. So we're going to start by adding 7,500 over a squared to both sides. So we get 1 is positive 7,500 over a squared. And then we can take, or actually we want to maybe from here, we want to multiply both sides by a squared. So now we have a squared is 7,500. And then we take the square root of both sides to find a. I want to write it like this: square root of 75 times square root of 100. Because we can write square root of 75 as square root of 5, or sorry, square root of 25 is what I meant to write. Square root of 25 times square root of 3. And then times square root of 100. So square root of 25 is 5. Square root of 3 is an irrational number, can't really reduce that or break it down anymore. And then the square root of 100 is 10. So our value for a is 50 times square root of 3. What we want to do now is make a sine chart for our derivative, and I'll explain why we need to do that now that we have our critical point. This function only has one critical point, and it is this one right here. Or actually, I lied. There's another critical point. We can see that we have a rational function. We have a variable in the denominator. A critical point could also occur for a value that makes us experience a 0 in the denominator, a value that would make this part of our expression have a denominator of 0. So our critical values are the following. Critical values, critical points, critical numbers, they all mean the same thing. A equals 0 is our first critical point because it means we're going to have a 0 in the denominator. And 50 root 3 is our second. So we want to make a sine chart for the derivative, a sine chart for s prime of a. And the reason why we want to do this is because it allows us to determine where our function is increasing and where our function is decreasing. If we had a graph, it would be easy to tell. If we had, I don't know, maybe something like this, we could tell that our derivative is 0 right here. And if we were to break it up into sections like this, and then also in the next two sections where the derivative becomes a 0 again, gives us more divisions, we can tell that our function increases until we get to this point, and then decreases after that, and then only increases after that. So we can find increasing and decreasing behavior from the graph, but we don't have a graph at our disposal at the moment, so we have to use other methods. And that's where the sine chart really comes in handy. Sine chart makes it really easy to decide where our function is increasing and where it's decreasing, just by taking the derivative. If the derivative is positive, our function is increasing. Likewise, if it's negative, our function is decreasing. We want to start by taking our critical points. And I put the dashed line there for 0, just to signify that whenever we have a is 0, this gives us an indeterminate value. We have a 0 in the denominator. Our function is not defined at this point. Our other critical point is 50 times the square root of 3. And I put a dashed line in this case just to show that this is a place where we have a 0 derivative. This is probably I think the only place where a 0 derivative occurs. So now it is simply a matter of identifying if each of these regions are going to have increasing behavior or decreasing behavior. So let's start with our very first region. So to determine if it's increasing or decreasing, we just want to pick any point below 0, anything in this interval. I think -1 would probably be easiest. So my goal is to find f prime of -1. No, sorry, s prime of -1 is what I meant to say. So we have our s prime of a right here. So I want to just plug in -1 for a. So we get the following. So we can see we have 1 minus a very, very large number, meaning that this is going to be negative. So this produces a negative derivative, which means the derivative is going to be negative in this entire first region. Which means that we experience only decreasing behavior on this interval. Our function only decreases. So we want to do the same thing with our next interval. So I want to maybe just pick 1. 1 seems pretty easy to work with. So I'm going to find f prime of +1. Plug in 1 for a, we get the same thing we had otherwise, the same thing we had in the last example when we had -1. This is also going to produce 1 minus a very large number. So once again, our derivative is negative, which means this interval is also going to experience decreasing behavior only. So now it would be really easy to assume that our next region would be increasing. In fact, it probably is, but it's good to be in the habit of testing things, because sometimes in higher math classes, things don't always work out the way you expect them to. Sometimes you'll see certain circumstances that make things behave in a really strange way, in a way you're not expecting. So it's always a good idea to check and verify everything before you conclusively find your answer. So we want to do the same exact thing. So what I want to do here is I want to pick a value that's greater than 50 times √3. But what the heck is that, though? What is that in decimal form? Well, let's do some figuring. Square root of 1 is 1. Square root of 4 is 2, which means square root of 3 has to be somewhere between 1 and 2. 1 point something. You can find it easily if you have a calculator, but we won't always have a calculator available. We have square root of 3 is between 1 and 2. So let's say we just round up to 2 then in that case. Let's say we pick 50 times 2. What if we pick 100 for our value? And it's just a quick way to find a value that 100% for sure is in this interval. 100% for sure is greater than 50 √3. So I want to pick 100 as my value, and then I want to do the same thing I did with the other ones. I'd like to find s prime of 100. So let's see, we have 1 minus 7,500 over 100 to the second power. So this would be 100 times 100, which would be 10,000. We can do a little bit of simplifying. We have a factor of 100 in the numerator and a factor of 100 in the denominator. So this simplifies to 1 over 75 over 100, which can be simplified further to 1 minus 3/4, giving us 1/4. Positive 1/4. So our derivative is positive in this region. It's greater than 0, which means our function experiences only increasing behavior. All right, so far so good. We've done most of the heavy lifting by now. Done most of the intense figuring and calculating. So now it's just a simple matter of taking a look at our Sine chart and then getting the information we want from it. So they're asking us to minimize this quantity. So we can take a look at our sine chart and determine where that minimum might occur. So if this were a graph, we know that it might look something like this. We would decrease, and then this is where we have a zero derivative. This is where our derivative becomes zero, which means we're going to have a flat horizontal tangent line right there, and then we're going to become increasing again. And this is completely unrelated. This curve I just drew, I'm not saying it's the curve of the function, but it exhibits similar behavior. And I just kind of used it to show you guys that we decrease, and then we decrease again, and then we have a zero derivative, and then we increase. So imagine we have a local maximum. We decrease some more, and then we get to a place where we have a horizontal tangent line, and then from there we increase. So it might be something kind of like this. So the fact that we have a horizontal tangent line right here, and the fact that we decrease until that point and increase after, is all the proof we need to definitely conclude that this is indeed the minimum. So that's why calculus is such a useful tool. It's only through differential calculus, through derivatives, that we're able to prove conclusively that this is indeed a minimum. Not done quite yet, though. All we've done is found the value of a that produces a minimum. Important information nonetheless. And I apologize for my handwriting. I know it sucks, but I'll try my best. Let me know if you have trouble reading anything. So we know that when a is 50 root 3, we produce a minimum. I wrote minimize. I meant for that to say minimum. Apparently I can't write either. So now what we want to do is we want to take this quantity and replace a. Or actually, you know what? We might want to start with our constraint, because our constraint is what we need to find b. We have a times b is 750. A times b is 750. Dividing both sides by 50 yields square root of 3 times b equals 15. B is 15 divided by square root of 3. And rationalizing our denominator yields the following. We have 15 root 3 over 3. Which simplifies to 5 times the square root of 3. So we have our a, we have our b. So all we really need to do now is plug them into the quantity to be minimized, quantity that we have already actually minimized. So a is this, and then we have plus 10 times b. So this expression turns into 50 root 3. So we have two 50 root 3s. So our answer is 100 times the square root of 3. This is our absolute minimum.